Next presentation, and this is another, say Googly, I would put it, or say Google X. Our Dr. Joe is from Wearables. Google X is now called Wearables. It's in the healthcare industry. He's an expert in what you call radio technology and applying radio technology to the. We talked about people, now he's talking to go and handle the animals. How to manage through the radio technology, tagging and all, the animals. That's what he's going to show us.
Thanks for the introduction. My name is Uei-Ming. I'm from Berry. Most of the biomedical projects are developing in the Berry, but I'm not supposed to develop the detail of our project. Just give an overview of the biomedical area, some example, some experience. It's not done by Verdi, but just overview if you have some idea. So in today's talk, I'm going to present 4 topics. It's what is data power, the whole system, and I will give some example for the animal experiment, and some example for the implantable devices. And last wearable devices. Actually, you can see all these topics is for wireless. Wireless means we are going to have a long-term data collections. And I'm not a data scientist, but we develop some systems for the data science and to collect the data. And the first one is the wireless medical system. You can see usually we bring the wireless medical devices because we want to have some long-term monitors. So that means we want to collect the data then by the wireless, and those we want subject breathing, moving. But the problem is for wireless systems, we need power and we need data. You can hear some presenters previously, the platform. But how to manage all the systems? Because, for example, if you want to have a high power, you can have a longer range. But the problem is you lost the battery, your power bank should be bigger. Or you want to put connectivities, that means you have bigger antenna, but nobody wants to have some bigger antenna. So there are several issues in the whole systems. First is antenna and signal processing and the sensors and the power. So for the wearable, for these wireless systems, the antenna size is very important. We want to have some optimized antenna to minimize the size. And the sensor is also important because usually, how do you collect the data and what kind of data is useful? It determines by the physicians. And another issue is if you want to do the signal process on the device or transmit the data out to the gateway and do the processing on the platform. That's another issue. So this kind of summarizes what I'm talking about because for example, if we want to do the signal or the data analyzed by the wearable device or some mobile device, that will consume a lot of power. But the good thing, we can see it real time. And but if we want to have too much data, that will use a lot of power. That's the several issues. Then we are moving to some animal experiments that we are going about. It based on the system we are talking, and this is how we implement it in the animal systems. This is the system. It developed by Georgia Tech, and it's kind of long-term monitor the animals. Basically, this system is we want to collect the biological data from the animals, especially the application used for the neural recording or neural stimulations. And so we want to have a long-term monitors, but we don't want animal carry the batteries. That's we need a wireless power. Wireless power, there are several wireless power ways. Basically, they use inductive link. for the RF signal for the wireless power. This is an example. They monitor the pressure, and actually there are some product on the market for the human. They can monitor your pressures, and the device is implanted inside your body and donate and through the wireless power or wireless sensing to detect. But like I said, the system we are working is for neural recording and neural stimulations. This is usually the neural you can see in our brain. There are a lot of channels. Right now could be 1024 channels that consume a lot of powers, and you need a lot of data. So currently, there are commercial devices. They use like the cables to collect data and provide power. You can see the animals is limited in these small areas. And some people, they use a battery. That's animal just put a jacket, carry the batteries. Another interesting topic is optic genetics. I'm not sure if you heard about this. So the goal is just stimulate the specific area in your brain, in the right brain. So they have doing the specific functions. But you can see even the stimulations that requires a lot of powers. So most of the animals, they are carried by these wires, but that limits the experiments. Because there are some previous study shows that why the limit area affects the experiment result. These are examples. If we put a subject just here in a small area, there's nothing. And they put a small toys or training wheels, or put a big area, you give a lot of toys. The growing of a neuron is totally different. So in the enriched environment, the growing of neurons is kind of like more realistic situations. Then the reaction is more realistic. So this is why the neuroscientists, they want to collect some data wirelessly through the experiment. So this is why several wireless power systems has been developed, like they use small cages. But again, you can see these small cages, the ammo is also limited in the small area. So this is why we developed the system they call the N-cage. Like you can see the wireless power through the bottom, so it's the floor, there's an antenna array, collect the transmit the power, and it also can have a data link, but a very low data rate. If we want to have a high data rate, this is through the RF link. So the part, for example, the neural for 64 channel neural recording, usually the chip power consumption is 15 milliwatts, which is a lot. So this is why we need a wireless power. Here is the system architecture, but I'm not going to details because this, as we collect data, power amplifier, and here is how we design the antennas, and can modulate and kind of each panels, so each antenna array can be modularized. So this is an example. Since you can see this antenna array can be modularized, and we can create our own array or maze. So the animal can freely move it, but it's been wireless power. Then we can collect all the data. Here is the magnetic field. You can see in the edge with some, it's not red color. That means the energy is being weak. So this is why we have to use the array to cover all the area. Here is the spec for the system. This is a real experiment result showing it's done by the Emory universities. And you can see this, we can, 4 panels, there are 4 panels, we just modularize it, put together. Then the small, the subject is here, and it's been wireless power. So here's a small video, you can see here, we put a subject here. There is no battery, just solely wireless power. And we use a LED for the indicator. So we can know where is the animals based on the wireless power sensing. There is also a small magnet, and the magnetic sensor can just monitor very accurate animals' movement based on this system. Another function is the closed-loop power. So this is because based on wireless power, we don't want to burn the animals, the poor subject always. So when we got sufficient power, we just decrease the transmit power. So it's automatic closed-loop power system. So the power level is kept in a certain space. And for example, we got if our voltage is low, then the transmit power, for example, if we get enough power, then the power amplifier, we don't need to have to transmit a lot of power. Then we already get a sufficient. So that means it's subject to be laid down the floor. So it already get enough. This is a short conclusion for first part. That means we develop a long-term monitoring systems to collect the data. Then the neuroscientists, they can analyze all the data because our neuron is like a 3D environment. They analyze the long-term data, they collect how the movement or activity for the subjects. And we also have the magnet sensors, just check the animals. Here is some future work. They are still working on it. So, like, for example, we could have 2 subjects or multiple subjects, or reduce how we create the environment for the neuroscientist. There's another examples for using. This is they call it the animal home cages. They do the experiments based on the small cages. So like the pharmaceutical companies, they test the result of the new drugs, or they want long-term monitors. But the problem is all the scientists, they have take out the data, and take out the animals, collect data, and put it back. It's very time-consuming. You can see in these pictures, there are thousands of subjects. And this is why we create systems, then you can collect the data. Here's another example. They call it a soundbird. The soundbird is they got a feedback from what they see, and they stimulate fire the neurons, and they want to collect sounds of here. You can see this is a video showing there's sound or they see something, and yeah, so they kind of collect data. Is because the activity is a closed loop, so we want to get a feedback from the activity and to see how the neurons work. The third topic is the long-term data collections. This is for implantable devices. The implantable devices, it's very common. It's more and more common nowadays. Usually people put a battery or wireless power. Battery is most common use, and but right now we are studying the wireless power. So, for example, you put a pacemaker in your heart. Then you don't have to change. Usually the pacemaker, you have to change the battery around 10 years. But that is painful because you need another surgery. So here is an example. There's a pacemaker or brain stimulations. Let's control like a Parkinson's disease. They want to stimulate the brain, then you don't have to like shaking hands or something. But you can see most of the part of the device, the battery occupies the area. So this is why some people are using the wireless power. Wireless power for implantable devices is more and more common. So this is like a neural ocular implant, but they are still using battery, but the battery outside. So it's just wireless power inside your device. And this is a retinal implant, just stimulated your eyes, so then can stimulate the brain, then you can see. And they also have a stimulator, just brain control. This is for severe paralyzed people. For wireless power, usually for efficient way is inductive link. So because we want to transmit enough power, so inductive power is options right now. And but problem is we also need for implantable device. We also have a concept of data link. Data link means you have to transmit data throughout the body. But usually the tissue can absorb all the energies. Then how to optimize the antenna and how to minimize interference from the power link is very challenging. So there are some examples. People use data and power coil. They are in the same plane at different frequencies. Or if you want to just minimize the data and power, just separate. But of course, you can see you have two data coils and big power coils that increase the size. And the antenna design is also challenged for the implantable device because, like I mentioned, our tissue absorbs the energies that equate our signal qualities. That's why this is proposed system. They call it multi-link systems. First, we have a data link. First, we have power link that's provide energy for the implantable device, and we also have forward link. Just give a command for the implant or back telemetry will collect data. For example, usually the back telemetry will collect data, like I said, for the a lot of neural stimulation or other functions. We need a wideband data collections. So this is application for the retinal implant. So we want to transmit the data and power through this short distance. It's around 1 centimeters. Then we transmit the data through here, give the power, then we will get data back. So this is a link how we optimize the link because most of the power consumption is in the tissue or free space loss. Then this is a result. Here is a result shows optimization result. So if you use an antenna, just put it outside the body. You can see in the free space. This one has the second one is not optimized antenna. You can see it has it optimized for the air, but it's not optimized for the tissue. And this one is optimized for the tissue. Then you can see in the air, of course, it optimized for the air. You can have a higher efficiency. But if we put exactly the same antenna inside our body, it's totally different because you can see it degrades a lot because the antenna is only optimized for the air, but the one optimized for the tissue get a lot of improvement. Then we are talking, that's the wireless power part. Then we move into the data. So there are several ideas for the data, minimize the interference. This is the concept of they call the figure 8 coil. Figure 8 coil is like you have two directions of the magnetic field. So if you put exactly the same coil inside on the power coil, it cancels each other. So that means your data coil and power coil won't get interference. Actually, figure 8 coil is being used for a lot of area. Like when we are in the traffic light, you can see you stop traffic in front of the traffic light. The figure 8 coil is also using for the sensing the vehicles. And this is two data coil design. One is figure 8 coil. Another idea is just perpendicular. You just use another magnetic field. Just you can see this magnetic field is horizontal, and the other is like vertical directions. This is also another option to have a data link. Here some experience results shows the alignment issue. At a perfect alignment, the power coil, we have minimized the interference between the power coils. Here's an example how we made the small coils. And we put on the top is an antenna. So it's, like I mentioned, it's for the back telemetry data. So we use a wideband spiral antenna to have a larger bandwidth to collect the data. This is just example showing the antenna design, but we have to integrate everything in the packages. And there are several challenges for the packages, how to integrate the analog circuit, RF circuit, or antenna, especially the biosensors. And this some figures show how we combine all them together. And hermeticities, we can't have to prevent the moistures. That's also important. So just give you a quick summarize because we can see this multi-carrier for the implantable devices is for the wireless power and for wideband bandwidth for low power circuit. And a lot of applications people are working on is for the human because we want to stimulate or record different positions because our brain have different locations has different functions. So this is why wireless power is very important, and we collect them all the data. The last one, the wearable device. For wearable device, right now people are thinking about wireless power, but the problem is we still have a challenge for moving even outside activities. So battery has been used. So a lot of companies, including Verily, we also has a lot of studies about wearable devices. And for wearable devices, the battery is being used inside the device. Then we can collect the neuron or eye movement or ear or wrist. I think wrist, I didn't list the example because a lot of people they are using the watch. It's been used. And fingers and arm and legs. I want to give you an example of the finger data collections. This is the picture shows the pulse. So you can see for older people or younger people, the pulse is different. This is because our heart is pumping out to the end. It will get a reflections because the body. So you can see several peaks in the pulse. I want to say is for the data analysis, usually people collect the, let's say, heart rate, or just basically you can see even Apple Watch or a lot of smartwatch, they are collecting the heart rate. But actually, the heart rate is based on this pulse. There are some interesting examples. Some people, they are analyze this pulse. So in the very old Chinese medicines, they found some relationship result of this pulse. So they are collecting the data. So the pulse shape would reflect your body, your physical activities, or women or men or activities. They kind of analyze this data to collect, you will say if you are too tired, your waveform could be different. And if women they have a period, and the waveform could be different. That's a very interesting result. This is why they want to collect the long-term and collect a lot of data for long-term monitor these collect to analyze to get some useful results. So this is why people that are using a lot of sensors, not only the pulse, there's a breathe or chest. Actually, is even the pulse waveform they found some interesting. It's not only collect the heart rate. If you put a frequency longer, and you can also monitor the breath, you can see the waveform is going up and down, and can monitor your breath. So this is why the long-term data analysis is very important for the data scientists. I'm not a data scientist, but we developed this circuit for them. And then they collect the data and translate the data for the useful information for the physicians. Usually we have to work with the physicians because they know what kind of data is useful. They kind of filter out some noise. That's very important. Another good example for the wearable devices, sport activities. You can see these are sport activities. They can monitor your movement, motions, and another application is the rehab systems. So have been studied more and more in these areas, especially for the medical areas. Then they kind of collect a lot of data because, for example, the human movement is not like robotics. You will see a lot of noise. Then how to filter out, or even use they call it machine learning, how to collect the correct data and translate the data out. This is been working. So this is some quick summarize. So for the wearable devices, in the future, the wearable devices should be comfortable. That means, like I said, should be minimized. And power measurement, you want small the size. Then, like I mentioned before, if you want to transmit a lot of data, that means the power consumption is very high. But if you want to transmit very limited data, the bandwidth could be an issue. And accuracy of sensors, so how we collect the data, is also important. And the last one is I mentioned for machine learning. Because the information is very noisy and so much data. Usually it's hard for a human, even a neural recording, it's hard to use a human eyes just collect the data. Then how we develop an algorithm to do the data analysis is very important. Because of time. Thank you very much.
Thank you, Dr. Uei-Ming, and fantastic insight into the brain. And we always think of light, but here is static LC circuit oscillating into your head and trying to figure out what's happening to your, we call it brain to compute and brain to brain. And I think we have next speaker coming later after the dinner. And there is Tina, I didn't see her, but Tina is going to talk about the AI and the B2I stuff and B2C stuff, so you will hear from her. At this time, do you have any questions for Dr. Uei-Ming? Okay, if not, let me just ask for the sake of asking, why do you use static LC circuits? Can't you use active circuits in the implanting?
Actually, it depends on the applications. So, for LC circuit, first inductive link is a power efficient way. So, you want to transmit a high power, then usually the LC circuit is the best option. Because, for example, like I mentioned, you want to collect a lot of neuron data. The antenna power is not enough. If you want to have another power, we have to transmit a lot of antenna power that's not sufficient. So efficient is most important.
That gives insight, so they don't want to do any power amplification inside the body. Interference is important. Thank you very much, Dr. Uei-Ming. Now I would call, is Professor Shobha there? I have been waiting to hear. She's not here. Who would like to come? Let me call Rajiv. Rajiv is the next, he's going to handle the post-lunch MC, post-dinner, sorry. And at this time, Rajiv, you should give the certificate to Dr. Uei-Ming. Just I will give to Rajiv to say.